an idea of how we're going to write and denote stress and strain in our tensor notation, let's look at some complex and biaxial stress states. So what happens when we're not in this situation where we're just pulling in one direction? What are going to be the strains and stresses that occur in this system, or if we have shear, or if we resolve, if we're looking at some plane of interest along some angle theta that's different from our kind of coordinate system that we've done so far, what are we going to do? Well, let's go ahead and actually let's do kind of a quick thought experiment. So here's my biaxial stress state, and we are going, so I have two stresses. So if I look at my stress tensor, I apply some stress in one direction, some stress in the 2 direction, everything else is 0. And we call this stress state a biaxial stress state, and more specifically, a plane stress state, because all of the stresses are basically all the stresses occur in one plane, the 1-2 plane. You could have stresses in the you could have plane stress in the 1-3, the 2-3, etc., etc. But here we have plane stress in the 1-2 plane. So we have some kind of unconstrained surface here, and so let's go ahead and let's think about a scenario where first we're going to stress in the x direction, or in the 1 direction here. So 1. And there's going to be some resultant strain. So if I apply my first step, a stress in the 1, there's going to be a strain in the 1-1 that's going to be given by this. So let's go ahead and break this down piece by piece. So I have a material here, and initially I'm going to pull it like this. So when I pull this material in this direction, sigma 1-1, the material is going to now like this, extend axially, contract laterally. So the strain in the 1-1 is just going to be given by, again, here we are in the Hooke's law regime. So sigma equals E epsilon 1-1, 1-1. So my stress, or my strain, is just going to be 1-1. Oops. Yeah, 1 over my Young's modulus. But we're also going to contract in this direction here. So my strain in the 2-2 is going to be given by, again, still the same stress, because what was our Poisson's ratio? Our Poisson's ratio was minus the axial, the lateral contraction over the axial stress, or excuse me, the axial extension. So if we rearrange essentially this expression, we could, again, we are looking and trying to solve for this, again, E22 is our lateral contraction. So if I want to figure out, so L is 2-2, this is 1-1. So if I want to figure out that kind of lateral extension, I'm going to have to multiply by that Poisson's ratio. So if I do that, I'm going to go ahead and rewrite this expression. So my E22 is equal to minus nu E11, and we know E11 is just this, so that is going to be equal to minus this in terms of stress as well. So lots of ways you can kind of rewrite and rearrange this. So this is the first step, again, because we're in a we're just doing a thought experiment here. We're going to get to the real expression you're going to use quite a bit. So that's the first step, stress in this direction. So now imagine that we then, in the second step, then pull like this. Well, again, what's going to happen to the material? It's going to extend like this, and as such. So now we have, in the second step, we have our strain in the 2-2 direction. And again, as I pull here, it's going to contract right here. And again, same idea, except now our Poisson's ratio is, again, minus, what's the lateral lateral component here? It's 1-1. What's the axial extension? 2-2. So if I want E11, I just rearrange and solve there. So when I figure out the total strain in the x and the y directions, i.e. the 1 and the 2 directions, you can now see that I will have an expression. So let's go ahead and rewrite those out. So we had for our first step that E11 is equal to this, and E22, this is kind of our first step, is equal to minus this 1. And then we had our second step, we had that E22 is equal to sigma 22 over E, and then sigma 1 is equal to minus nu 22 E. So if I look at my strain in the 1, 1, that's going to be equal to what? It is going to be equal to sigma 1, 1 over E minus nu sigma 2, 2 over E, and E2, 2 is going to be equal to sigma 2, 2 over E minus nu sigma 1 over E. That's it. So that's my strain in the one direction. I could also rearrange and write out the total stresses in the 1, 1 directions, and I could extend this to the 3D state as well. Now, one of the, this is, again, we are dealing right now with isotropic linear elastic materials. But one of the nicer expressions that I could use, and a more general expression, is going to be this equation right here. Right here. This epsilon ij. This is the most general expression for how I could rewrite and write out an expression for my strain. So let's think about if I'm in the following stress state. So let's say I'm in 1, 2, 3. So let's say, for example, I'm pulling here, here, and I have, actually, yeah, let's do that. So I have in my stress tensor, I'm going to have, actually I'm going to do, so I have stress in the 3, 3. I have my stress in the 2, 2. And I'm also going to do, so this is 0. I'm also going to do, I'm going to have strain. Actually, we'll deal with that a little bit later on. So actually, let's do that right now. Actually, let's do that later on. So let's look at getting plane stress here. So I have sigma 2, 2. So if I want to figure out my epsilon 1, it's just going to be equal to 1 over E times. So do I have my sigma 2, 2 times 1. Is there any scenario here where I does not equal J? So if I is 1, 1, here, undo this. Excuse me. So I'm looking for where I is equal to 1 and J is equal to 1. You can notice here that this is a Kronecker delta. So this means that if I is equal to J, my Kronecker delta, Ij equals 1. When I does not equal J, Kronecker delta is equal to 0. So in this scenario, I is equal to J, so this is 1. So what's going to happen here? I'm going to subtract by all of the KK. So these are the same kind of notation, the same indices or counters. So we're going to, I want to write out the strain in the 1, 1 direction. So 1 is equal to 1 over E. And then I'm going to write out sigma 1, 1 times 1 plus nu. And that is going to be minus nu times sigma, basically sigma 1, 1 plus sigma 2, 2 plus sigma 3, 3. Right here. Because this is saying iterate this variable over each of these kind of values here. So all the KKs. So I have 3 dimensions, so I can only have my KK, sigma KK values can only equal this, this, or this. So you can see this kind of reduces, and this expression here is going to cancel out with this one right here. So we're going to left with epsilon 1, 1 is equal to E times sigma 1 minus nu times sigma 2, 2 plus sigma 3, 3. And we know that these exist in this expression. But if I want to find, again, now, okay, what is the value for sigma 1, 1? This is just 0. So if I have those stresses, I can calculate my strain in the 1, 1. Let's go ahead and do the strain in the 2, 2. It's just going to be same thing. So now I'm going to be 1 over sigma 2, 2 minus nu. I'm going to go quick here. Sigma 3. That's it. You could kind of double check that math. What if I want to do epsilon 1, 2? Well, that is just going to leave me with 1 over E, my sigma 1, 2, 1 plus nu. Now, I does not equal J, so my Kronecker delta, this is 0, so there's no term here. So this is just it. That's my expression. Sigma 1, 2 times this 1 plus nu. So nice, really beautiful expressions. Now, again, no matter what my stress tensor, whatever those values are, I can now just calculate out and see, okay, here's my expression and here's what's going on, or here's my expression for strains. So I would highly suggest using this. To me, is the most important equation, not Hooke's law. This is the one that we're going to use all the time in this course. So we could really kind of verify, and you can kind of see that this expression matches. So let's go back to our expression here. We wrote out this. We now know from our expression that E11, if I have, in general, it's going to be this. So 1 E times sigma 11 minus nu times sigma 2 plus sigma 33. But in this scenario, our sigma 33 was 0. So you see, we basically get this expression again. Same thing for sigma 22. E sigma 22 minus nu times sigma 11 plus sigma 33. That's equal to 0. And you get the expression again. So from this thought experiment here, we obtain and recover this expression right here. So ignore that first kind of little mind gap, and this is the expression that we're going to utilize. So next time we're going to get into a brief discussion of, actually we'll go through it right now. Now, we've been assuming, and actually it's kind of explicitly stated here in the notes, we are basically developing theories for an isotropic linear elastic material. Isotropic means that our material will exhibit the same properties regardless of the direction. So if I'm looking at this plane versus this plane versus this plane, it's going to behave exactly the same. My material properties don't change depending on kind of my crystallographic direction. But, so basically my E is constant if I'm looking here, 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 the 45, my material properties don't change. But unfortunately, this isn't true for a lot of materials, and specifically titanium 6Al4 vanadium, titanium 6Al4, titanium 64. It has, at certain temperatures, a HCP structure. It's a hexagonal close packed. So I'm not even going to try to attempt to draw it, but basically it looks like an, again, hexagon. And along kind of, you have this kind of A axis and B axis, but you'll have a C axis here, this long C axis. And your material, my E, my stiffness along that C direction is much larger than in these other directions. So my material properties change depending on, again, this crystallographic direction. So you have to kind of deal with these materials anisotropic. So your material properties are going to change as a function of this expression. So instead of kind of this idea of Hooke's law here, where we could just kind of rewrite this expression like so, we are going to have to deal with this monster of an expression. So we're going to have to relate our stress and strain tensors via this fourth rank tensor. So and this is kind of really confusing notation, where C is our stiffness matrix and S is our compliance matrix. And again, these have this relationship that your stiffness and compliance matrix are equal. So if we were basically, if we weren't assuming that, again, we're isotropic and cubic and having only 6 independent components, the full anisotropic fourth rank stiffness and compliance tensor will have 81 independent components. Very, 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 very nasty. Now, most materials have some symmetry that are going to reduce that component, and actually you could kind of rewrite and make a quick change in notation as kind of described here to kind of make this a little bit nicer. And you could see this is our infinitesimal strain theory, this annoying factor of 2 that always pops up. And you could rewrite that whole 81 components, excuse me. You go from 81 components just with this change in notation. But notice that this is now not a tensor, it's a matrix. So we went from 81 though to 36 components. So you could rewrite, and again, these represent Young's modulus, all different Young's modulus in different kind of directions of matrices. So these are 36 independent components, but we can reduce these further. So based on kind of considerations of strain energy density, so our energy or our elastic strain energy, that basically our area under the curve, our stress matrix, our stress, stiffness, strain, that these matrices must be symmetric, i.e. this is equal to this. we could reduce this 36 down to 21 increments. So what it's saying is that if this is symmetric, sigma j is equal to sigma ji. If that's symmetric, then again, it's kind of the symmetry, right? So when we looked at our second rank tensor, we said sigma 1, 1, sigma 2, 2, sigma 3, 3, that sigma 1, 2 is equal to sigma 1, 2, sigma 1, 3. We're symmetric around kind of, again, that diagonal component. So if our matrices are symmetric, or tensors are symmetric, then we could reduce it down to 21 values. So you could reduce even more, but again, you'd have to take basically a symmetry course. If you want a good discussion of this kind of based on symmetries and this Onsonger's theorem, and you can actually look across a really great description in Sam Allen's Kinetics of Materials book, the best description I've ever come across. You could kind of show, and there's proofs that if I have a triclinic material, that symmetry, again, the symmetry of my material, again, higher symmetry, you're going to have basically kind of these lower and a higher degree of symmetry, a lower independent kind of coefficients. So my triclinic has the lowest symmetry, so I have all 21, monoclinic 13, and then all the way down to 9 for orthorhombic. These are going to be some really important for composites, some polymers as well. Tetragonal 7, and then for cubic, I'm just going to have 3 and 2 if I'm isotropic. So this is just kind of a fun, supplemental, material in case you ever get to dealing with materials that are anisotropic. So you can kind of go through and look at. I've included some of these kind of derivations and kind of see, okay, how can you figure out or prove these kind of 3 independent elastic component and get relationships between them. So you could kind of read through this at your leisure. But again, the key thing that I want you to kind of come away with is that when we're writing stress and strain, if you're given any complex stress state, we could write the strain using this equation right here. We will use this all the time in this class. So be prepared to rip those out very, very quickly. Epsilon 2, 3, I know that's going to be equal to 1 times sigma 2, 3 plus 1 plus nu. It needs to be this quick. We cannot be thinking when we get to the exam. You should be able to rip these out very, 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 very quickly. So sigma 1 plus sigma 2, 2. It has to be this quick. So practice those. You practice those on your problem set, and then I will see you all in the next video where we get, again, you can kind of look at some of these values. We are going to look at our first kind of mechanics example, strain without stress. How's that possible? I'll see you in the next video. Thanks. Have a good one.